How's everyone doing? Alright, so I just want to talk about entropy. I shouldn't have put in more depth, in slightly more depth. I want to make it a little bit more concrete. So this is the curve for entropy of just one binary random variable. So this is like a biased coin toss, and this is how much the y-axis of this graph is how much entropy there is in bits, and the x-axis is, say, the probability of heads, and it's symmetric because swapping the probability between heads and tails, if you remember the formula for entropy, which I'll show in a minute, all that amounts to is reordering terms in a finite sum, which will never change the outcome. Okay. So, if, say, it comes up heads or it comes up tails every single time, there is no uncertainty. If it comes up heads and tails exactly half the time, that's one bit of uncertainty, and likewise if you get all the way over to the tail because of symmetry, notice that there's perfect left-right symmetry. Then obviously when you get over to the right endpoint, entropy is also, or uncertainty is also equal to 0. Entropy and uncertainty are synonyms. Context for this video: x is, let's say, a binary random variable that's a reserved term, means something specific. X has heads with probability p, or tails with probability 1 minus p. The entropy of heads is minus the sum of probability of p, or p, times the binary logarithm lb of p, plus 1 minus p, lb 1 minus p. Unit of that is a bit, and that I'll call either h of x or h of p, interchangeably. And I'm very sloppy with the notation about h of whatever, but this is what I mean. So, if it's just one coin toss, this is what it looks like, with a biased coin, and the x-axis is the bias of the coin. So how much uncertainty is there in a coin toss, given the bias of the coin? Okay. So, I introduced this playlist with Huffman trees, and that's kind of where this first kind of whatever module is getting to, is the connection between uncertainty and compression. So what entropy is the minimum average length binary encoding you need for the random variable. So what happens, you build out a tree like this for your discrete random variable, so the nodes at the end of this could end up being letters of the alphabet, and they have a probability distribution associated with them. So in the Huffman tree example, there were all the characters in the file, and at the they have a probability distribution associated with them, and what you want to find is the tree that encodes that probability distribution that has the minimum average code length. And what Huffman proved, so first of all, it's kind of a result that we'll get to eventually that's kind of obvious in context, which is that entropy is the minimum average code length. You cannot design a code such that its average code length is lower than the entropy. And a Huffman code always has the property that its entropy or that the average code length of the Huffman tree is between the entropy and the entropy plus 1. So anyway, so for one coin toss, heads, tails, you encode that with 0 and 1, that's 1 bit of entropy. So let's walk through the calculation, because these calculations are actually super helpful in seeing why the formula makes sense. So h of 1/2, 1/2, that's minus, just plugging in the formula for entropy, half times the logarithm of a half, plus half times the logarithm of a half. Well, half plus a half, that's 1 logarithm of a half. Well, by the proper 2 is equal to 2 to 1/2 is equal to 2 to the minus 1. By the properties of logs, this minus 1 can pull out, and it cancels with the minus sign here. That's why the minus sign is there, and you get log of 2 in bits, which is 1 bit. Cool. For two coin tosses, you have the same thing. So 2 heads is 0, 0. Head tail, that's 0, 1. Tail head, that's 1, 0. Tail tail is 1, 1. Two coin tosses, 2 bits of entropy. So Same thing going on here. So h of 1/4, 1/4, 1/4, 1/4. That's 1/4 times the log of 1/4 4 times, which is of course equal to minus the log of 1/4, so minus sign here. And then by the properties of logs, that's equal to the binary log of 4, which is the binary log of 2 squared, which is 2, because the 2 pulls out, log of 2 is always equal to 1. Log base 2 of 2, obviously. Same logic, so n coin tosses have n bits of entropy. Generally here, right, so there's going to be n levels of depth in the tree, n bits of entropy. So n coin tosses n bits of entropy. 2 to the minus n is the probability of each sequence. So 2 to the minus 2, that's 1/4. That's this many, that's 2 branches, 2 bits of entropy. So 2 to the minus 2, 1/4. So n is equal to 2, that's 2 bits of entropy. So n coin tosses, n bits of entropy. 2 to the minus n, that's the probability of each sequence. So entropy of n coin tosses is minus, right, there's 2 to the minus n times the log of 2 to the n, that's each term, and there's 2 to the n of them because that's how many outcomes there are. Put a minus sign there. 2 to the n cancels with 2 to the minus n, and then you get, oh, I skipped a couple steps, so then you get log minus the log of 2 to the minus n. N minus n pulls out, cancels with the minus sign here. And n times the log of 2, that's always equal to n, and again, n bits. So hopefully now entropy makes a little bit more sense, and the connection with encoding trees is a little bit more clear. Probably the next video I'm going to use this basic idea to, maybe I will do this, maybe I won't, is to explain why a comparison sort can only have order of n log n. So that'll probably be the next video. Thank you for watching. Please tune in next time.